Welcome to this explainer. Today, we're taking on literally the ultimate heavyweight champion of the universe, Earth's gravity. It's this massive, invisible obstacle that just keeps our feet planted firmly on the ground. But humanity's greatest technological triumph? It's our ability to build machines that can punch right through it. So today, we're going to explore exactly how a rocket engine generates enough thrust to leave the ground, pierce the atmosphere, and finally reach the silence of space.
17,500 miles per hour. Just let that sink in for a second. That is the sheer, eye-popping speed a spacecraft absolutely has to hit just to escape the relentless pull of Earth's gravity and stay in a stable orbit. To put that into perspective, that is roughly 10 times faster than a bullet fired from a high-powered rifle. It's honestly just a staggering velocity.
So the crucial point we really need to figure out is, how do we actually do it? How do we generate that much mind-boggling power? I mean, it's one thing to build a machine that goes super fast horizontally on the ground, right? But pointing a massive metal cylinder straight up at the sky and forcing it into the vacuum of space, that requires a level of engineering that almost defies logic. So let's break down the actual mechanics of how we conquer gravity.
Okay, Section 1. The problem of Earth's gravity.
You know, every great story needs a great antagonist, and for space exploration, it's gravity, for sure. It's this invisible, relentless force, and it literally never, ever takes a day off. Before we can even dream about exploring the stars or planting flags on the moon or sending rovers to Mars, we have to solve this massive physical problem first. Gravity is constantly pulling everything toward the center of the Earth. So to lift a rocket weighing millions of pounds, you must push up with a force so violent and sustained that it completely overwhelms that constant downward drag.
Which brings us to Section 2. Newton's third law explained.
To beat gravity, we actually rely on a rule written centuries before the very first rocket ever took flight. You've probably heard it, Newton's third law of motion. Basically, for every action there is an equal and opposite reaction. It's absolutely the foundational secret to rocket thrust. We all know the classic balloon analogy, right? You blow up a balloon, untie the end, the air shoots out one way, and the balloon violently flies across the room in the exact opposite direction. That's just Newton's third law in visceral, everyday action. And that brilliantly illustrates the exact dynamic happening at the base of a rocket. Think about the action here. You have superheated exhaust pushing down out of the engine nozzle with incredible force. The reaction? The rocket gets pushed up. A lot of people think it's pushing against the launch pad or maybe pushing against the air, but actually no, which is a good thing because there's no air in space. It's purely the violent downward action of that exhaust directly creating the upward reaction that lifts millions of pounds of metal and fuel right into the sky.
Let's zoom in a bit. Section 3. Inside the rocket engine.
So how do we practically create that massive downward action? Well, a rocket engine is essentially a highly controlled, continuous explosion, and it happens in 4 incredibly fast steps. Step 1, the propellants, that's your fuel and your oxidizer, are pumped into a combustion chamber under extreme pressure. Step 2, ignition occurs, sparking this ferocious chemical reaction. Step 3, that reaction creates gas that expands super rapidly, generating intense heat and pressure. And finally, Step 4, this expanding, high-pressure gas really only has one place to go, and that's out the bottom nozzle. By funneling that expanding gas through a narrow throat and then flaring it out, the engine accelerates the exhaust to hypersonic speeds. It literally turns raw chemical fuel into pure physical force.
To really wrap our heads around the extreme energy scale required for this continuous explosion, consider this slightly absurd fact. A heavy-lift orbital rocket engine consumes more fuel in just a few seconds than your average family car will use in multiple years of driving. It's a literal fire hose of explosive energy. The pumps inside these engines are moving thousands of gallons of propellant every single second. Honestly, if your car burned fuel at that rate, you wouldn't even make it out of your driveway before the tank was bone dry.
All right, Section 4. Reaching the final frontier.
Scaling these basic mechanics up to meet orbital requirements takes an unbelievable leap in power. Think about a modern commercial jet airplane. A massive, incredibly powerful machine that easily carries hundreds of people across oceans. It's impressive, right? But compared to an orbital rocket engine, it's night and day. A large jet engine might produce around 100,000 pounds of thrust. But a single large rocket engine? We're talking millions of pounds of thrust. It absolutely dwarfs the jet.
This massive leap in power is exactly what's required to make that wild transition from atmospheric flight to actual space flight.
So, you might be asking yourself, why does all of this matter to me down here on the ground? Well, because this exact physics equation, action and reaction, scaling up controlled explosions, is responsible for the vital technology currently floating above your head right now. Powered by this immense thrust are the GPS satellites that navigate you to a new restaurant, the weather monitors that warn us of approaching hurricanes, and of course, the brave astronauts living and working in the vacuum of space. Every single time you check the weather or pull up a map on your phone, you are directly benefiting from the mechanics of rocket thrust.
We've mastered chemical rockets to conquer Earth's gravity, for sure. But the universe is vast. To travel deeper into the cosmos, to reach neighboring stars, chemical rockets simply won't be fast enough or efficient enough over those massive distances. Which leaves us with this final thought. What new propulsion technologies will take us beyond our solar system? Will it be ion drives, nuclear thermal propulsion, or maybe something we haven't even dreamed up yet? The foundational physics of thrust will always remain the same, but the future of how we generate it? That is wide open. Thanks for exploring this with me today, and stay curious.